So hello everyone, in this video we are going to talk about the logistic regression. It is a new machine learning topic. So let us just start. So as the name suggests, regression, but still this is a classification algorithm. It is used to classify or predict the classes based on the features of those particular classes. So let us just start. So by the end of this video, you will be able to have a clear idea of logistic regression approach with all the sigmoid curves and all the basically whatever function is required, hypothesis function, its significance, cost function of linear regression, how to minimize those, everything we will talk about in this video. So what is logistic regression? It is basically a statistical method for analyzing a data set in which there are one or more than independent variables that determine an outcome. So it is actually a classification algorithm, as I told you. So before starting with logistic regression, let us revisit our sigmoid function. So this was a function which I have already explained in our mathematics for machine learning video, whose link you can also find in the description. And so let us just revisit that slide. So it is a very useful function which follows the S curve, which saturates when the input is very large or very small. It is like logic gates in physics. So you can, as you can see, this is the function phi z or sigma x, we can also say that. So it is 1 by basically 1 plus e to the power of minus z. So if you see, if you tend this z to infinity, so what will happen? It will tend to 1, and if you tend this to 0, so it will be 0. If you tend this to minus infinity, it will be 0. So it saturates when the value is large. So it works like the logic gate in physics. We can say that it is on or off condition. So if z is greater than 0, we are more towards the 1 than towards the 0. So we can say that our class is 1. So we are basically predicting our class. Suppose we have two classes, 1 and 0. So we can just say that if our phi of z is greater than 0.5 or z is greater than 0, it is more towards the 1, and therefore there is more probability that our class is 1. So in this sense, you can also consider this as a probability function. So in machine learning, the sigmoid probability activation function, it is basically. So it has a unique feature. You can calculate its derivative without actually calculating its derivative. So what do I mean basically? Without using the operator dy by dz, you can easily find the derivative of this using this property. You can also easily prove that using some basic mathematics. You can easily prove this formula, and so this can be treated as one sort of probability function. It in the sense that it ranges from 0 to 1, and probability also ranges from 0 to 1, but it is not exactly the same in the way that sum of all the probabilities at a point is 1, but it here it may not be 1 at all the points. The sum may not be 1, right? But it is a sort of probability function which is used to predict classes, the classes being 0 and 1. So let us understand that what exactly is this hypothesis function. So this sigmoid function we actually use as the function hx, and that is our hypothesis function. Now in x we actually use m transpose x. So why we are using m transpose x? If you remember, our equation was something like this: y equals to mx plus c for one variable, and for n variables we can write it as y, this is n minus 1 variable basically. So y equals to m1 x1 plus m2 x2 till mn xn, we can say this, where y is our predicted y value, isn't it? We have all learned this in linear regression, polynomial regression. We have understood this clearly. So you may ask that why is m transpose x? So let just consider m to be a row matrix. Then m transpose will be a column matrix of all the coefficients. And what will happen if you just multiply these two matrices? it will be the m1x1 plus m2x2 plus m3x3. So it will be the sum of the product. So it will behave like a dot product basically, right? In dot product also the coefficients get multiplied, corresponding coefficients get multiplied and added. So we use m transpose x is basically the reason why we are using this. And m transpose x is basically this, you can see y predict, this is the m transpose x, and that is what we are substituting in our hypothesis function. So what is the, let us just get a feeling of what this function actually does in real life. So if hx is greater than 0.5, then m transpose x greater than 0, and then we get a linear decision boundary. So what is basically meant by this, see, h of x is greater than 0.5, as I told you. If it is greater than 0.5, then it is mostly towards 1, and then m transpose x, which is the z here, this m transpose x is greater than 0. Then also from the last equation, what is basically m transpose x is this linear equation. So if I tell you m1x1 plus m2x2 all the way till mn(xn) greater than 0, this is what? This is a inequality which is basically giving a linear boundary. So m transpose x greater than 0 is basically a linear boundary, linear decision boundary. So if we plot two features x1 and x2, note that we are not plotting any y here, we are just plotting the features x1 and x2, and on the basis of those features we are plotting the data points on our plot. So this is the curve of let's say we have two variables x1 and x2, then m1 x1 plus m2 x2 equal to 0. This is the line corresponding to that, and this is h of x equals to 0.5, and let this be h of x greater than 0.5, then any point in this, means this entire region to the down below this line, this entire region would be corresponding to h less than 0.5, or and the above region of this line would be h of x greater than 0.5. So this is basically the feeling, and this is the separation boundary. So we can say that if all of these out of the all the fruits, let this be the bananas and this can be the apples. So this is just referencing into various classes. So we just understood that using logistic regression, how, what is the basic, what is the math, and what is the sense behind that math to just separate two classes, right? So later we will also talk about how to separate more than two classes. So let us just see what is the cost function. So instead of MSE, mean squared error, which we saw in linear regression, here we use something known as cross entropy as our cost function. So what is this cross entropy basically, and what would be the harm if we use MSE? So if you see, the cost function was 1 by e to the power of 1 by 1 plus e to the power of minus z. So if we use that, if we just differentiate and just sum of squares all those, then there won't be any particular, that was linear regression. Due to a linear curve we get a particular minima, but here we will get many minimas. So this cost function we defined is it as cross entropy, and that is the cost is basically, this is not cost t, it is cost is minus logarithm of hypothesis function if y equals to 1, and it is minus logarithm of 1 minus hypothesis function if y equals to 0. So how to get a feeling of this? So let's just take an example. Consider that y, the actual label, is 1. This is the actual label if y is 1, and we classify it as e is tending to 0. So then we are misclassifying it, right? If we are classifying something as e where e is tending to 0, then our cost function will be minus log of e, because this h of x is the hypothesis function, which is ultimately the thing into which we are classifying. So hypothesis function is the thing into which we are classifying. If we are classifying it as e, then the entire hypothesis function is e. So if minus of log of e will be a very high value, positive value, right? Because e is tending to 0, and like if the actual label is y, and if we classify it something tending to 0, the cost increases significantly, and the cost will reduce is if we classify it to nearly 1. So if minus log of 1 is basically 0, so the cost will be exactly 0 if we just classify the correct value. So let us just combine this piecewise cost function. So we'll combine it on the next slide. So you just see this graph. This blue line represent minus log of h, and this red line represent 1 minus log of h. As you can see, as we tend to 0, as we go towards 0 value of h, means we are misclassifying our class and our cost increases significantly. And it is just the opposite if y we have y equals to 0. So if y equals to 0 and we are going towards 1, we are misclassifying it as 1. It is supposed to be 0, we are misclassifying it as 1, and therefore our cost is getting increased towards the value of 1. So this is the essence which you should understand. So we just combine the two cases. So earlier we get a piecewise function, we are just combining those. So after combination we will get this. You can also see, let's say y is 0, then we had this function from the earlier slide. If y is 1, then we had this function from the earlier slide. So this representation is the piecewise representation of, this takes care of both the conditions of the piecewise function. So this cost function can also be labeled as the error function for our model. So for our model, this can be just the error function. So that is basically the cost function. And for all the data set containing x and y, we will just sum up all those values. So we will get some e as a function of x and y if we just do summation of all our data points. So the only parameter we can have it, we can vary in our cost function is h of x, and there in the variable m shown below. So this is the h of x basically. And here also, like linear regression, our aim is to improve accuracy of our model. So we can just differentiate and equate it to 0 partial derivative. So using gradient descent approach also we can do that. So if use from gradient descent, we know that I have explained you in detail that in this way the gradient descent actually works. So now we need to find this partial derivative of with respect to mth data point coefficient, the error function. So whatever error function I showed you, if you differentiate it, you can do this math on your own. It will be quite simple. It may be lengthy, but it would be really simple to just differentiate this function. You need to just, with respect to m of j, you need to differentiate this entire function, and then you will get this value where m is the sum of, basically the number of values, and m of j represent the jth data point. So in this way the optimum values of m can be reached, and using linear regression, using this gradient descent, we will reach one of our minima of our error function. So our aim was to reach a minima of error function, which we have reached. So yeah, that's all from this video. In next video we will extend our knowledge of this linear regression further. Thanks a lot.